Okay, so the next talk will be Tour the PostgreSQL Data Types by Andreas Schabong, and he will introduce himself, I guess.
So, can you hear me? Does it work? Okay, welcome. Yeah, let's talk about some of the Postgres data types we have. Short note about myself, my name is Andreas. I work for a company called Pivotal. Before that, I worked for EMC, and Pivotal is actually a subsidiary of EMC, so I moved between EMC and Pivotal and so on. And I work on Greenplum and Postgres projects. Okay. How many of you are using Postgres? Okay, other way around, how many of you never used Postgres? That's good. Anyone knows more than like 10 data types in Postgres? Okay, that's like 10 hands. That's good. This talk is for you. Anyone who is here to get a seat for Simon's talk? Unfortunately, this talk is cancelled. I'm sorry. Okay, first question. How many data types do we have in Postgres? I take answers. 40. 63. Any more?
Only one.
Only one. That must be VARCHAR. Yeah, if I look into PG type, in my database I get 361 right now. Unfortunately, this also includes any table types we have, because they go into the same table. And it includes any references to another type here. So if I include this one, I get 82 data types in my database. Still a lot. It's a long list. We don't want to look at all of them, because about half of them we don't care, like what's the TS range or what's an SQL identifier and so on. But we have some very interesting data types here we want to have a look. Luckily, the Postgres documentation, which by the way is very good, provides a list of data types we want to use. And this table in Postgres 9.6 comes with 41 data types. Okay, well, we asked this question, how many data types you're using. Most of you are not even using 10. Let's see what we have for you. So we have text types in Postgres, we have numeric types, dates, and so on. We even have some special types handling JSON or Boolean, binary data. And we start with text types. How many do we have? Any idea? 2, which is? Well, in the end, we have varchar, we have char, we have text, but internally they are all the same. It's one data type internally. It's just external representation. And by the way, unlike some other databases, all text types in Postgres are case sensitive. So if you do a like and you want to have a case sensitive comparison, you need to use I-like, not like. If you use varchar or text, you can store strings up to roughly 1 gigabyte of text. If you specify a char without any length specification, it's actually just 1 byte. Probably not what you want to do. So with char, you want to specify a length. With varchar, it's optional, and it does not include any white spaces at the end. There's an interesting case. If you look at the white spaces at all, I have 5 white spaces here, and I cast them to varchar and char 5 and 10 and 1. And you see the lengths here. If I have my varchar 5 and my varchar 10, they all end up with 5 white spaces here. If I have casted it to char, I end up having 10 chars, because in char, if I specify a length, Postgres will actually fill up white spaces until the specified length. Okay, how does Postgres store any text type, or by that any variable length type? Back in the good old days, we only could store any string up to 8 kilobyte roughly. We have so-called pages, and every page is 8 kilobyte size. And Postgres aims to store about 4 rows minimum in every page. So it's roughly 2K we can have in a table. It also defines how many columns we can have in a table. It's 1,500 columns per table, because every row has to fit in a page. So how can we store a gigabyte of text in 8 kilobyte? Well, we can try to compress it. We can increase block size to a gigabyte. Or we can just go and have text be a pointer into yet another table where we just store multiple rows for every text. That's what Postgres is doing. It's totally transparent for you, but it means you have 2 tables now. If you do a vacuum in a database, occasionally you see it's not only vacuuming your table, but it's also vacuuming so-called toast tables. You see them flowing by if you want to vacuum them both. Because then you have to increase the page size to 1 gigabyte. Yeah, you have a pointer into yet another table, which is also using 8 kilobyte pages, but it's using multiple rows until you have your gigabyte or whatever data you want to store. Which also means we can have variable lengths for char, varchar, or numeric, and so on. And Postgres is handling this for us. So what about this varchar or CHAR255? Whoever run into such a table definition, having a varchar 255? About 20. Why? Any ideas? I haven't heard Oracle before. I have heard Informix before. I have heard SQL Server before, because back in the 90s, they only could store 255 bytes in one column. So this problem doesn't apply to Postgres. If you run into a table with char or varchar 255, go and ask the question why someone defined a table this way. It probably doesn't make sense. It might come from that 255 is actually 2 to the power of 8 minus 1, or 8 bits. And MySQL has an interesting limit. So if you have an index key, it can be 3 times 255 bytes, not more. Not like in Postgres where you can have a gigabyte for index. They can only store 3 byte UTF-8, and this limits them to 765 bytes. Yet another reason why they have 255 here. Okay, let's move on to numeric types. How many do we have here? So we have integers, we have floating points, and we have numeric. This can be kind of confusing, because if you come from Oracle, most people on Oracle use numeric to store any kind of integers and such, but you don't want to do this in Postgres. Most likely you want to have an integer, not a numeric type. On the other hand, I've seen customers storing any kind of money data in a floating point, which is kind of funny if you run it in auditing later on, because floating point, it's always rounded up or down. It's never exact. Okay, we have small int, which can store 2 bytes, which requires 2 bytes and can go from minus 32K to plus 32K. Most likely you have an integer, which is minus 2 billion up to 2 plus billion, so it's always a signed integer. And we have a ridiculous large big int, which uses 8 bytes internally. Now, if we have tables which mix small int, and you have multiple small int columns, you want to look how you align your table. Like if you have small int, integer, small int, integer, you would expect it's 12 bytes. It's actually 16 bytes, because it's always aligned to 4. You can't start an integer on 2 bytes. So Postgres is actually losing 2 bytes here and losing 2 bytes here. If you just rearrange your table, small int, and then integer, integer, you have 12 bytes. If you have a million rows, okay, it's a few megabytes. If you have a billion rows, we're talking gigabytes here. Then we have floating point numbers. So we have real, it's 4 bytes, which has a precision up to 6 digits, and we have double precision, which goes up to 15 digits. Always means it's a rounded number. It can store almost everything, as you can see here. So we have 6 digits here, and okay, it shows us the correct number here. Once I add one more digit here, you see it's rounded. And this will really hurt you, so I have 7 digits here, and it gives me back a totally different number. So if you try to store any kind of like money or such in a floating point number, your results will be wrong. Don't do this. The same for double precision here, so 15 digits, it's okay. It gives me back the same number. Once I go to 16 digits, it starts rounding my number. And same problem, I have 60 digits here. It starts giving me back another number, it's rounded up here. So what can I do if I have to store something like money or such? I have to use numeric. Numeric has a precision up to, oh, let me go back, sorry. We also have a money type in Postgres. You don't want to use this one at all. There are like 2 users in the world who use this in total. I think it's 2 or 3 times that it was called deprecated, it was resurrected, patched again. Well, it uses 8 bytes of storage, and it can store up to 92 quadrillion. In comparison, it's still 4 digits less than we have this current US debt. So US still have a way to go. If you want to store money, you really want to use numeric. Numeric data type, you specify your precision by saying, okay, that's my total number of digits I have, and that's my number of digits I have after the decimal point. So I have 10 here, you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's a bit confusing, but you get around it. On the other hand, numeric is handled in software, so there's no hardware support like if you have integers. Integer can be handled in a CPU register. It's not the same for numeric, so it'll be slower. But you get your precision. Okay, anyone knows this guy? No? Not in person? Yeah, I think so. It's been a while. Anyone knows this puzzle? How many or how much is it? -1. Yes. So if you try this with a double precision here, 2 to the power of 64 minus 1, double precision gives us this very inaccurate number. If you try the same one with numeric, 2 to the power of 64 using numeric, we get a very exact number here, and it's still only using 20 digits. We have 980 left. So if you ever find a use case for all of the 1,000 digits here, please let me know. Okay, let's move on. We also have sequences. In other databases, you might heard about it. It's called auto-increment or so on. If you define a column in Postgres as serial, Postgres will automatically create a sequence for you and set it as a default value for this column. It will also attach this sequence to the table. So if you drop a table, it will also drop a sequence for you. It doesn't have to be, can be. Sequences by default start with 1 and increase by 1. But you can change this. So you can have a sequence which does steps 5 or goes backwards. or starts with 1,000, whatever. Some people use this if they want to count values in a query. They just create a sequence in their query in a transaction, count something, and then drop it. Works this way. A sequence is not transactional. So anytime you receive a value from a sequence, it's gone. It's never rolled back. So you will have gaps. Like if you roll back a query and you received 50 or 100 sequence values, they are gone. There are a few functions for sequences, like you can use current val to get a current value, but it will only work if you already used or consumed the value in your current session. If not, this will return an error. You can request the next value of a sequence, so this will just increase by 1 and give you back the value. And then you can use current val to retrieve the same value over and over again. And you can set a sequence to a new value by just using setVal. And some people like to get rid of the gaps they have in their tables or in their sequence, like when they had to roll back a huge transaction and they have a huge big gap. You can easily do this by saying, okay, setVal and get my maximum value from my sequence. Never relay on a sequence name. Usually it's sequence, table, ID, and a prefix of sequence. But it doesn't have to be. There's a function which you can use, pggets_sequence. You specify a table name and a column name, and Postgres will return the sequence name to you. And then you can go and say, select star from my sequence, because it acts like a table. And it gives you all kinds of information, like what's my current value, can my sequence actually cycle over? Like if I have a small serial number, I can go up to 32K. What happens if I go over this? By default, Postgres will just reject it. You can change it and say, okay, I want to go over and start from the beginning. Or at any point, if you have questions, please just ask. Where's my microphone? What? PG,
Can you please repeat the question?
I will do. PG gets the sequence gets you the old sequence? The own sequence, yeah. If you want to see which sequence is used, you have to look at the default value for this column. So you have two things. You have a sequence, you need a sequence name, and you have a default value. And in Postgres, if you actually specify something for this ID column here, it will not use the sequence. So if you want to see which sequence is used in a column, you have to look at a default value. You can also go and have a sequence used in several tables, like a global counter. This works as well. So it's not limited to one table. Okay, what's this? Any ideas? How did you figure out this one? 90 degrees south latitude. It's southward. Okay, what's the time there right now? That's a valid answer, yes, all of them. Actually, that's wrong. UTC is wrong. Okay, let's find out. We have several date and date times and interval data types in Postgres. So we have a timestamp with and without time zone. Usually people use the shortcuts here, timestamp and timestamp TZ. We have a time with and without time zone, obviously without date. And we have a date, obviously without time zone, because it's just a date. Never go and use a varchar or char to store timestamp. Please don't. if you use a time zone, a timestamp with a time zone, Postgres will actually handle any kind of summertime, wintertime changes for you. I'll show you a few examples. It will not handle any leap seconds for you because the operating system has no idea about leap seconds. It's not stored anywhere. It happens occasionally, like last New Year's Eve, but it's not stored anywhere. Okay, here we have a simple timestamp. Actually, I use the date here and cast it to a timestamp, so you see I get back my midnight value for the same day. I even can use this silly formats they used in the United States by having a month first and then my day. Postgres can do it. Now I use timestamp TZ here with a time zone. I specify a time zone UTC, and you see there's a difference. First of all, I used PM here, and I specified it's 3:25 PM, and it ends up giving me back 5:25. That's because my time is always returned in the time zone I have on my database server. Not where your client is, but the time zone your database server is running in. So if you want to have less trouble, set all of your database servers to the same time zone. If not, it might be confusing. Right here, it's 2 hours difference. You can see it's August, it's summertime. I get 2 hours difference here. Here I use the date in winter, in December. You see it's 1 hour difference, so Postgres gets the daytime saving right. This works with any time zone name we have in our operating system database. So I can just specify a time zone here by name, and it knows how to handle any daytime saving for this time zone, including all the changes they have, like Russia a few years went to summertime and never went back. And ever since then, they just stay on summertime all year, which is nice, except they have no summer. If you just specify a number for a time zone, obviously, there can not be any daylight saving time handling. So if I want to return a date in a specific time zone, like this year, it's always returned in my own time zone where my server is running. I can also set my new time zone here by just saying set time zone. Then it's returned in the time zone I specified here. So Postgres is doing all the math for us. We don't have to do it. It's very handy. But it's quite complicated to set a time zone every time. So I can just say, give me a date back in this specific time zone. This can be part of a query. Couldn't be any easier. Okay, I can also do math with dates and times. Like here, I have 2 timestamps, and I get back the difference, which is an interval now. I have 4 days difference between these 2 timestamps. Or like here, I just turn them around. I get -3 days because this one is smaller than this one. Works with times as well. So it's not only days, it also works with times. I can have my difference in days and times between 2 timestamps. If you want to know how long back someone inserted something in the database, just do a timestamp minus now, no, now minus timestamp, and you get back time since when this happened. Okay, another interesting use case here. I have February 28, and I want to know if the date was if the year was a leap year or not. I just add an interval of 1 day. If it's a leap year, I get back February 29. If it's not a leap year, I get back 1st of March. Come again? It was. It was. It is. You can divide it by 400. It was. Are you questioning Postgres? get out. Okay, we have 2001, 1st of January minus 2000, 1st of January. So I get back 360 days, which means 2000 is a leap year. Again. I use 2002, 1st of January minus 2001, 1st of January. I get back 365. So 2001 is not a leap year. Okay, coming back to this question. What time at South Pole? South Pole is Scott Amundsen Station. Actually belongs to the US, but it's supplied from New Zealand. So for easiness, they just use the same time zone as New Zealand, which is NZ. So by now we learned how to query time for New Zealand. Select now at time zone New Zealand. But this is, well, it's not good enough, at least for us, because South Pole got its own time zone. So we can actually query, select now at time zone Antarctica South Pole. And if you look into your operating system database, you see that we have like 9 or 10 different time zones defined under Antarctica. So every station down there got its own time zone, usually aligned to which country is operating this station. There was a question? The question was if I can use this construct at table creation time to show date always in a time zone. No, I'm not sure, but I don't think so, because Postgres is storing times in UTC. It's always a question of transformation once you retrieve a value. But feel free to try it out. Okay, let's move on to some hipster stuff here. Well, XML is no longer hipster. We have JSON for this now. So it's actually something from the 90s where you could define a document and describe a document in a certain structure. And Postgres allows you, if you have compiled in an XML library, to store XML native in your database and validate if it's a valid structure or not. It will validate the syntax, like if opening and closing text are correct. It will not validate any schema definition, DDT. You can store a whole document, or you can just store fragments of an XML document. It works both ways. I'll show you in a moment. Unlike in the standard, Postgres is always assuming the encoding you specified in your client encoding. These days, most people use UTF-8. Not all, not everyone. So it's always assuming that the document you transfer is encoded in the same client encoding you have specified for your database, except if your client encoding is actually SQL ASCII. Then it's using whatever specified in the XML document. And you cannot search in XML data types. You can retrieve them, but not search in them. So I have a few examples for you. We use XML paths to store a document. Here we have a full document using XML, and you see it returns my full document here. I can also store just a part of an XML document. And if I want to retrieve it and use it somewhere else, I can use XML serialize, have my XML content here, and I get back a string, which I can use in my application. Okay, but now for the real hipster stuff. We have JSON in Postgres as well. It's used in many web frameworks these days. I think every Internet of Things device you have which transfers data, it's using JSON. A number of this NoSQL database like Cassandra and MongoDB and so on use JSON native. And Postgres can do it as well. Why not? We have two different data types here. We have JSONB, which will decompress whatever you store in it and use a parse structure. And we have the order JSON data type, which will store whatever you write into it and will decompress and validate it once you retrieve it. And unlike NoSQL databases, everything you do with JSON and JSONB in Postgres is transactional. So if you roll it back, it's gone. Very simple example here. So I have my string here. Because I have JSON, I need to quote it here for JSON and just cast it to my JSON type so I get my data type back here. I can also have arrays. So I specify my array here, the number of values. And you see I get a full array back with all of my types. I can also use key value pairs, which is what JSON databases or NoSQL databases do usually. Key value, comma, key value, comma, key value. And I get my result back as a key value pair here. Okay, that's easy, but I can also look into my structure. So I can select, let's say, my key number 2. No, it's not number 2, my key 2, which belongs to the string number 2. So I only retrieve this element out of my JSON data type. Or I want to compare whatever I have in my database. Is this value in my JSON string I have in my database? Of course. I can use this operator and just look. This is here, yes. It returns true. Or I can see if this value or this key is in my data somewhere. DEF, yes, it's included here. I get my true back. I can also look up a key, if a key is in my data or not, because we know JSON is all about not having a structure of my data, so I don't really know what is in my data. If I want to figure out if there's something, if there's a specific key or a specific value in my data, I have to look it up, I have to verify it. If I have a structured database like Postgres, I know what columns I have in my table. It doesn't work this way in NoSQL. Good. One of the more advanced features we have, we can actually use an index on JSONB types. I can actually take someone a picture and send it to get hash, please. So we have a GIN index, which is generalized inverted index in Postgres, but it only works on JSONB, not on JSON. What I can do, I can create an index on my table, specify my values I want to index here. You see, I just access this name column here using GIN. And then whenever I query my table here, my name field in it, it will use this index to speed up my query. Which other database, NoSQL database, can use an index on JSON? Good. Let's move on. We have a few more. So we have a real Boolean type in Postgres. If you have anything which is supposed to store true, false, please use a Boolean, not a small int. I've seen this before a few times. So we have a so-called Boolean in a table, and we want to migrate it, and we end up with values like 257. What does it mean for a Boolean? You can use values like T or yes or no to store the values, but Postgres will always return either true or false. One of these two. And of course null, if you have it. So, one of the more interesting use cases here, I can have a partial index on a Boolean column. Well, I can have a partial index on any column, but here it makes sense. So let's say I have a log table, hundreds of millions of entries, and occasionally there's an error. I have a Boolean flag here. So most likely I'm not interested in the 99% where there's no error, but I really want to find all my errors very quickly. So I define myself an index on, what? Forgot my index definition. Microsoft PowerPoint has encountered a problem. I'm sorry. company. I'm sorry. I had JSON here. Okay, I just generate my data here. I have like 2% error values in my table. And if I have a conditional index on my column, I can use this index to find out, here's my index, where error is true. And I can use this index to find all the values where my error is true. And in comparison, let's look at the size of this index. My full index on this table is roughly 3,000 pages, and my conditional index is 57 pages. And out of this roughly 3,000 pages, 2,700 I will never ever use because it's my 98% of non-errors. I can't use this one. Good. We also have a bit data type. Makes sense if you want to store config values like true, false, and don't want to span one Boolean per column. So you can have multiple bits in one field. So we have bit, which is a fixed length, and we have bit varying, which is a up to this length you specify here. If you don't specify a length, it's always a bit 1. It's like a Boolean. And you can use all the logical operators we have, like and, or, and so on these values. So I have a table with my bit field here, and I can actually use a bit operator in Postgres to specify bits, so I don't have to do the math and use my decimal value. I can have Postgres storing this for me. Like here I have my data and I use an AND. Obviously I only get back the bits where in both values in my data, in my question here, bits are set. If I have an OR, I get back all my bits because it's either set in data or set in my query. I can have XOR. I can do all the bit operations we know from C, like I shift to left here, which basically means it's multiplication by 2. You see it's 21 here. I shifted it by 1, so I get 42 as a result. Everything in a database. I don't even have to pull out my data for this. And I can search for specific bits in my field, because that's what we do with databases, we search in it. So I want to find this bit, and I get back my data where this bit is set. Obviously I get all the other ones as well, but I don't care about them. Okay, have you ever stored binary data in Postgres? Or any databases for that matter? There's way too many arms. Why are you storing binary data? Images? Well, some people have to do this. Postgres has a binary data type for this. It's called byte A. And if you just want to store binary data in text, there's a problem. Postgres is written in C, and in C, a string ends with a binary 0. No bit set. If you try to send this to the database, you get a parse error at some point because your string ends here. Well, all the programming languages we have, like Python, Perl, Java, whatsoever, they all have functions to handle binary data. Well, I'm not showing any examples here how you can transfer binary data in a database. Please look up the documentation for the programming language you have. There are functions how to store and retrieve binary data from a byte A column. Please don't try to write your own parser. I've seen this. But Postgres has two different types how to present binary data. So the old format is escape. If you set byte A output to escape, you see we get escaped here. But it's very hard to parse because this can be anything from 1 to 3 or no escaped values. So a while ago they changed it to hex format where every value is a 2 byte hex value here. Actually, it's a 1 byte. So they all have 2 digits. It's very easy to pass, and it's quicker, by the way. We also have network address bytes, 3 of them. So we have inet, which stores any kind of host and optional network. We have CIDR, which only stores a network definition. And we have a MAC address field, which can store in 6 bytes a MAC address. So we don't want to go and use like a char or VARCHAR or anything to store IP addresses, because then you have to deal with IPv4 and IPv6 addresses. Postgres can do it for you. We have the right data types. Any kind of log parsing you do, any kind of network data you want to store, please use one of these types. Or like here, I store an IP address in inet, or I just store an IP address without a network definition, so I get back my /32. And here I just store part of a network, and Postgres will make an assumption what kind of network I'm looking for. So it's a 24 8-bit for the network. And again, if you do log parsing or such, I can use an index on such a column. So I have my inet table here. I can create an index on it, and I store a number of values here, and just want to find out which of these values belong to a certain range. Or I can say where IDR is in my range here, and you see I only get 2 out of the 3 values back I had here, and this query is supported by an index. So it should be very fast. There's my index again. Good. Last but not least, we also have arrays. An array is not really a data type, but it's a combination of types. So you can store multiple different types in an array. It can have any dimension. It can be multidimensional. It's very flexible. Think about it like it's JSON in one column. Before we had JSON in Postgres, people used array to handle this. Sorry. So here we have a 2-dimension array. It's my first dimension, my second dimension here. And if I select this as an array using the array constructor here, you see I get my 2 values, and in my second dimension here. I can also ask Postgres how many dimensions I have. So it tells me, okay, this is 2 here. I can ask for any element in my array, which makes it very easy to access whatever I have. So I just want to have this first element here. Or I want to have my elements 2 up to 3. So it will return these 2. Yeah, it tells me how many dimensions I have, and it tells me what is my length. So in this case, I ask for my total length here for the first element. It's 2, so I have 2 values in my array. So I can really loop over whatever I have in my array. And of course, I can search in my array, or I can say, okay, if this element is def, it returns true because it's in my array. I can prepend and append to an array. There are many more operations. Please look up in documentation, but these are the more interesting ones. It's a bit confusing because prepend actually has this parameter before the array, and append has it afterwards. If you think about it, it makes sense, but you really have to figure out which one it is. You can create a string out of an array. So if you want to use this one in your application, just use array to string, or you can create a table or a number of rows out of your array by just using unnest. Good. Last but not least, ever created your own data type? Well, I did. We have a few options here. We have a composite type, which is just a combination of different types. We have an enum type, and of course you can write your very own data type, but you have to write some C code for it. And you can use a few extensions we have, or a few more like postgres and so on. Let's quickly look into this one. So I create my own composite type here. You can see it's a type. I actually store 4 different data types in my type and use this type as yet another type in my table. It's a very simple example here. So I have 2 different currencies. I have a date and a value. And I just go and store my conversation rate between euro and US dollar. And for every day, I can have 1 row in my table holding all the data together. And of course, I can select it. It returns a row. I can also just pick certain values I want to have out of my composite type. And last but not least, enum. Enumeration is really a list of values, and you should consider if you need an enum or not, because this list should never change. Give you a good example. How many different gender values do you know? How many? 17? Any more? Well, Facebook defines 56 right now. So if I wanted to create a gender type, think again. You can create a type like here as an enum. I have my 4 different values here. Then again, I can use this type as a data type in my table. I can insert by using the values into my color column here. I can also select by using the colors. So it really does a one-to-n lookup for me in the background. Good. That's it for here. We have a few more. You've seen we have like 40 more data types. We did not look into all of them, but it's an overview of the most common used you will find in Postgres. Thank you.
Okay, so we have time for 1 or 2 quick questions. Please speak in the mic.
Thank you. Right at the beginning, you said you can lose space to alignment requirements of the columns in a table. Now, I seem to remember that years ago, the layout, the physical layout of a table was decoupled from the logical order of the columns. So I thought this problem was solved, wasn't it?
No, you have this in databases which have columnar storage. But in Postgres, it's just aligned the way you have it created. It's all in one page.
One more question.
Hey, hi, thank you for the great talk. I have one question. Will it ever be possible to use indexes on arrays or use other people's primary keys as fortune keys in arrays in the same way as it would be in normal database fields?
I think many people just moved on to JSON over arrays. Because it's functionally it's better than in arrays. And you can use all the fancy index stuff in JSON, which you can't in arrays.
Well, we are out of time basically anyway, so thanks, Andreas, again.
Thanks.